Oh, hang on, you can't hear. There we go, that's better, isn't it? All right then, so just to remind you, those who missed Monday, we've got the midterm this week. And with the midterm, as I mentioned, is that you have to make an exam. And with this exam, you've got to, I'm just trying to think and move at the same time. You've got to have 20 multiple choice questions with 5 options for those questions. And somebody asked me the other day saying, can we have some of the above, all of the above as options? Yep, sure, that's all legit. Then you've got short answer questions, usually worth about 2 to 4 marks, and then a long answer win, which is usually more than 15 marks. And as you know, in traditional exams, 1 mark equals 1 point, doesn't it? So it's essentially a level of detail. Now, somebody else also asked me about the course objectives. And, you know, when we develop courses, you've got an objective at the end of it in terms of learning objectives. And the only way you can really test them, well, you can obviously integrate them into the course, but the only way you can really test them is through examination, isn't it? So when you're developing your questions, you look at the course objectives and say, well, so for example, objective 1's about history, isn't it? So how would you test the history? Would you say, a history lesson like saying who discovered pasteurization or things like that? But I won't like say spoil your kind of thing, but you get the idea. And so you look at the rubric, and then, as I mentioned, the deadline is on Friday at midnight, so you can submit it then, and I'll go through them, and we should be good. And you don't need to supply the answers with the exam. There you go. I was toying with the idea of giving each of exchanging the exams and letting you do them, but I thought it'd be too cruel, isn't it? So don't worry about that. All right then, so we're going to move on with this. So when we left it on Monday, we were talking about the foodborne illness and foodborne pathogens, and we came to the immune system. Like, I don't mean you to be immunologists, but what you'll notice is as we go along talking about pathogens, and pathogens have their own little tricks. I always call them like little superheroes, if that makes any sense, in that they've all got a special power, and some of these powers, how to avoid the immune system or how to use the immune system to their advantage. That's why we need to know a little bit about the immune system as we go along. So, as I mentioned, I'll just do a quick recap because I think I left it halfway through last time. We've got beta cells and T cells, and these are basically our immune system, the mechanics of it. Not all of it, obviously, some of it. Now, the B cells are the antibody factories, and what they do is that there's got lots of random receptors, beta cell receptors. And these random receptors will eventually bind to an invading pathogen, coronavirus, if you want to be topical. So once it's bound, what it does then is that it expresses a protein, an MHC2 protein, major histocompatibility complex 2. And what this forms is a docking station for the helper cells. And when the T helper cells dock, they release cytokinins, which is like the switch of the immune system. That's when all hell breaks loose. Basically you get fevers, you get proliferation of the beta cells and T cells, as we'll talk about, and they produce all these antibodies towards, for example, coronavirus, whatever you're invading. And as you can see, we use vaccinations in order to prime the body for invasion again. So we have memory cells. And one of the big challenges with COVID, if we're going to stick to COVID, is that when you activate the immune system, if you overdo it, it can be deadly. Basically toxic shock syndrome, which isn't that basically causes the body to self-destruct. But anyway, to get to a more not more cheerful things. So macrophages are another way of triggering the immune system. So what the macrophages do is they ingest the microbe, Salmonella, we'll go back to the traditional pathogens, digests it, and again, it expresses this protein on the outside, this complex. And this complex binds with the T helper cells, releases cytokinins, more B cells produce antibodies. It also produces these cytotoxic T cells, which are basically go round looking for infected cells or host cells and just blows them up. You know, literally a scorched earth policy. And you can see how things can get out of hand. So, you know, back to the macrophages then. With the macrophages, what happens is the bacteria captured, and then they get in this vacuole, and then what they do, or endocytosis as I call it, then these lysosomes come and start digesting the pathogen of interest, be it salmonella. And what it does is produce these fragments, because it's digested the bacteria, and it expresses these on the outside. Again, this MH2 sort of expression of the protein in order for them to dock. And once they've docked, they then have this immunoresponse, isn't it? So we've all suffered from foodborne illness, isn't it? So when we suffer from foodborne illness, what we find is that we get, oh, I don't think it's gone wrong with the internet. Oh, so it seemed to have stuck there. I don't know what it was. So when we get foodborne illness, what happens is that we get this fever, doesn't it? And with this fever, what we have is, oh, something's going wrong with the internet. Yeah, so it happened to the internet there, but don't worry, we'll get to the point. Seemed to just freeze, but anyway. Well, these things happen on, just don't need them, isn't it? All right, I think we're still recording, hopefully. I hope you can see something. All right, so it's live TV. Right. Right, I think we're good now. Yeah, all right. So yeah, like I said, the macrophages digest the foreign protein, express the proteins on the surface and then trigger the immune system. When the immune system's triggered, they release cytokinins, and these cytokinins start modifying the metabolism because you've got a lot of cell proliferation going on with the beta cells in there. And so what happens is you get vascular dilation, and you start getting a sweat, and that's all to do with the metabolic activity. And obviously the increase in temperature can kill off some of the pathogens as well, in addition to the person who's suffering from it. So with the immune system, you've got to kind of be a bit careful in that it can cause self-destruction. And this is one of the big issues when we come to vaccines and things like that. So in terms of foodborne illness, there's different modes by which illness is caused. Intoxication is where we ingest the toxin, and we'll talk about that. Infection is where you ingest a viable cell, and the other one is toxico-infection, where you ingest the viable cell, which then produces toxins. So we'll go through all these three in turn, and we should be have an idea what's going on. So, as again, intoxication is when you ingest toxins, and these toxins typically are released into the food system. So you don't need to eat the actual bacteria itself. You just eat the toxin that's being produced by it, and they're called exotoxins. And when we come to talking about other sort of ones that cause toxico-infection, they're the ones that have the toxin associated with the cell. They're called endotoxins. So typically then what we find is that with toxins, as you probably guessed, it's all preformed. So it starts acting once it gets into the body. And these can be very quickly, within 30 minutes. But other times it can take a progressive time for the illness to illustrate itself. And we've got examples of that with Staphylococcus and one with Clostridia. And the symptoms can stretch from mild to literally lethal, as we'll talk about. Now, the bacteria, some of the some of the moles as well. The toxins we're interested in are things like Staphylococcus aureus toxin, the botulinum toxin, which you probably know as Botox and things like that. And you get mold mycotoxins. And we talked a bit about this in the unit 2, I think it was, where molds can produce these secondary metabolites and they're usually antimicrobial. Now, when they're good, they're called antibiotics, but when they give you side effects, as in they're toxic to our cells, animals, or plants, they call them mycotoxins. But there's another toxin that you encounter, which I haven't included, but let's see if you can see which one it is. So which of these statements are correct about phycotoxins? So phycotoxins have been in the news just recently, but what are they? Are they produced by bacillus? Are they associated with grain, associated with seafood? Is it non-toxic, or is it none of the above? Let's wait for some more. Right, so we'll see. All split decisions. Well, what it is to do with is to associate with algae blooms. And so the algae blooms, because of climate change, etc., polluted waters, they can produce this toxin, which can get associated because it accumulates in seafood. It can accumulate in things like oysters and things like that, and it can cause these toxic effects. So there's been about 2 or 3 sort of recalls and outbreaks linked with this toxin over the last 2 years, which I suppose in a way is associated with climate change, but that's another matter for another day. So what we'll do now is we'll take each toxin or each bacteria pathogen in turn. And as I mentioned to you, well, as we go through the sort of different pathogens, you just look to see what makes them special. What's their kind of superpower, if you want to call it that. So we'll start with Staphylococcus aureus. So Staphylococcus aureus, as you know from your kind of first year micro, you look under the microscope, it looks like a bunch of grapes. That's its kind of characteristic. It's a gram-positive, and its special properties are a few. One is that it's very tolerant to low water activity. It can grow down to 0.88 water activity. So it can dominate on occasions where there's high salt, for example, whereas others are inhibited. Now, it is inhibited by refrigeration, and it's moderately pH resistant, but it likes neutral pH to grow. It can, it can exist at the sort of lower pHs, but it definitely prefers, if there's nothing else there, nice warm temperatures, room temperature, and it can proliferate. And once it proliferates, that's when it produces toxin. So it produces toxin once it's growth. So you'll see in growth sort of modeling is that you'll notice it's time for the Staph aureus to grow in order to produce a toxin, which is fairly it's not fatal, but it's certainly effective at low concentration, about 20 nanograms, induce illness. Now, the thing with Staphylococcus, it's the way it kind of evades the immune system is that it's got an enzyme called coagulase. And so when we get a cut or it gets into our bloodstream, what it does is use this coagulase to get the thrombin from our blood and coat itself. Now, as it coats itself, it's a bit like having a disguise. It can go around the body producing its toxin everywhere without being detected by the body itself, because if the body detects itself, it's friendly. It doesn't see an invading pathogen. Now, in addition to coagulase positive, you can also get coagulase negative Staphylococcus aureus. And coagulase negative Staph aureus aren't as virulent, they're not as virulent as a coagulase positive. And these are the ones we find on our skin, are basically our hands, our nose, our throats. And we used to do, we did a lab each year where we look at people's handprints. We would do a hand washing exercise where we ask people to wash their hands, press them on a plate, and what they get is these yellow colonies coming up. And these yellow colonies are typically Staphylococcus aureus. And what they do is they reside in your skin. So if you're a carrier, it doesn't mean to say you're unclean. It's a natural thing. It's Staphylococcus have adapted to your skin microflora and becomes integrated. And it's in your throat and it's in your nose and ears. It also causes mastitis in cows. And that's associated for around about, I would say, 10% of milk losses, because once Staphylococcus gets into the actual teat, then there's problems, isn't it? Because it's going to colonize it, produce toxin, and that milk will be contaminated, in addition to other changes. It's on our skin, pig skin, but the important thing is the toxin is very heat resistant. So essentially, what happens is that once it's produced, you could boil it, microwave it, and it doesn't decrease. So once it's produced, you can't destroy it within reason. All right. So what on that basis then, what would you do if you discovered Staph aureus from a raw food? Not worry, as cooking would destroy it. Would you irradiate it, add antitoxin to the product, discard some of the above, but not all? I think I gave the answer to this. I keep doing that. Right. I think everyone knows. Well, I think everyone knows this, and could like. Oh well, there you go. Yeah, so you definitely would discard it. As I say, cooking doesn't destroy it. Even irradiation doesn't, because it's a small protein, and there's no antitoxin. So yeah, you would definitely discard it. So Staphylococcus aureus produces this toxin, but there's different forms of this toxin. And this means it's what we call toxinotype. So it's the same toxin in a way, but slightly variable. So we separate Staph aureus based on the toxin it produces. And the Staph aureus entotoxin A is the most common. So this is what we encounter. So if you've been to a restaurant Super Mario's on Stone Road for some odd reason. Every time I ask this question in class, that's where they come up with. I don't know what it is about Super Mario. I should be careful because they'll probably sue me. But you've gone for a dinner and you feel nausea straight afterwards, and typically that's going to be Staph aureus because that's how quick it acts. And so the Staph aureus A is the one that SC, as we call it, the Staph aureus enterotoxin A, is the most significant in foodborne illness. There are some that's used as biological weapons, where you inhale it and it causes, and there's other ones associated with animals. But the most interesting one in my mind, not the most relevant one, but some of the most interesting one is this enterotoxin H. So the reason why enterotoxin H is interesting is that in Japan, there was a big outbreak. About 200,000 people were affected by it. And what happened was that there was some milk that got contaminated with Staph aureus, and it was essentially left out at temperature abuse, room temperature, where the Staph aureus group produced a toxin, and then they used the milk to spray dry it, and therefore you had instant, not instant formula for babies, but dried milk. And when it's dried milk, as you know, got a long shelf life, and they distribute it all over Japan. And like I mentioned, it caused something like 200,000 cases of illness. And it just illustrates that how Staph aureus toxin is very robust and things like that, and what can happen. Now, the way the toxin works is that it uses our immune system against us. In that we talked about this MH2, the major histone compatibility complex, which binds to these helper T cells, which send out these cytokines to activate all the immune system. Well, what the Staph enterotoxin does is act as a super antigen, and we'll come across these as we go along. And what they do is trigger the immune system. So this is what gives you that vomiting reflex, isn't it? Your immune system wants to get rid of everything or toxin that's in there. It gives you fevers and everything. So that's how it works. It basically stimulates the immune system. And by doing so, basically causes us to be ill, but it's short-lived. Basically the body just wants to recover from it. Now, as I mentioned to you, pathogens by their very nature don't like to compete with competing bacteria and microbes. So they like it when it's in their sort of Goldilocks zone. And as I mentioned to you, the thing with Staph aureus, it likes protein, and it's quite resistant to low water activity. So you'll notice it in products which have got high protein and a low background microflora are most likely to be held at room temperature. So what we have is things like hams and meat, soft cheese, slightly salt, puddings and custards, cream-filled cakes, and cream sauces. All these are literally associated with Staph aureus outbreaks. Now, there was a story, and Jim Chen will tell you this, because this was his finest hour, I think it was, Jim Chen being the director of public health in Toronto. So the story goes is that when we used to be in non-COVID times, we used to have an exhibition, down in the CNE, isn't it? And those who have been there, I think we've all been there in one way or another, they've got this food court and they have all these exotic foods from all over the world, so the kind of thing. Well, on this expedition, in 2013, I had the Cronenberg, and it makes my stomach turn just thinking about it. It's turning already this morning, as it is. And so basically it involves a croissant with a hamburger, with a donut. And to make it Canadian, they put this maple bacon jam on top. So the person who was making this, basically ripped off the idea from someone in New York, and he gave it to this bakery to make. Now the bakery is used to shelf-stable products. It's a bakery, but what they did is they made this maple jam, which, as the name suggests, is maple syrup, bacon, and something else, which I'm not sure what else it was. But they left it at room temperature. And they left at room temperature, and the bacon contained Staph aureus. It gave a nice environment for it to grow, which it duly did. And to make things worse, in the expedition centre, they left this maple jam on the top. And lo and behold, people started getting sick very quickly within an hour. over 280, I think it was in the end. And the public health were called in and they were looking around, because when people get sick, you think, well, it's not always microbial, it could be something, chemical. But I think it was Jim, one of his investigators, noticed the last jar of maple bacon jam in the fridge, and they took it out, tested it for toxin, sure enough, sky high. And like I say, it was Jim's finest hour. That you can ask him about it. But it illustrates about temperature abuse, doesn't it? So as we mentioned, then it produces this massive vomiting reflex. You get sometimes diarrhea. It's your basic immune system starting up to get rid of the sort of invading toxin. Usually non-lethal. You learn from experience, and you come down again. So typically, roots, it's to do with handling. So if we sneeze, if we direct hand contact on high protein foods, and commonly what these outbreaks would be associated with is the buffet. So for example, when you go to a wedding, you've got the buffet laid out at room temperature, then you go to the wedding, come back a few hours later, and that gives enough time for the Staph aureus to grow to produce toxin. So it's all those things, and like I say, reheating doesn't destroy it. So in terms of protection, what you tend to do is just have no direct hand contact. So if you are having direct contact, wash your hands. The 2-hour rule we talked about before, this is really related to Staph aureus. So you keep hot foods hot, cold foods cold. And when you're doing an investigation of an outbreak, we can use that clue about this sudden onset of illness amongst sort of people who are consuming it. And we can use that evidence and say, well, it might be intoxication. But then you look at the foods on the menu, and if you see things like cream cakes, high protein, you look for those, and then you can you kind of decide, putting two and two together, to find out where the outbreak came from. And what you tend to do is you screen the food for toxin rather than the bacteria, because as I mentioned to you, when the bacteria is long gone, the toxin's still there. And so the toxin will be there in higher copy numbers than the bacteria, obviously. So that's what you do. And some kind of side routes to Staph aureus. You might have heard of MRSA, methicillin-resistant Staph aureus. This is the one that when you get infection, you actually have to cut it away because it's super drug resistant. There's a few like that. And the other one is about the toxic shock syndrome. This is where, for example, you get a cut and 2 or 3 hours later you drop dead. And this is where your immune system literally gets triggered and goes into self-destruct mode. So, yeah, I could tell you a few stories about that, but I think I'll be digressing. All right, now we go on to another one, Clostridium botulinum. So Clostridium botulinum is one of the most virulent pathogens we encounter. With botulinum, it produces this neurotoxin, which I think it's one nanogram per kilogram is required to cause illness. And as we know, with Clostridium botulinum, is that we use it in a cosmetic treatment, Botox. And there was some instance last year where I think there was an untrained or unlicensed beautician, I think we call them, who was administering this Botox toxin and causing all these sort of intoxication. But anyway, that's a digression. Now, the thing about Clostridium botulinum is that it is a gram-positive. It does form spores. And the thing with Clostridia botulinum is that it's a bit like the lactic acid bacteria, in that you've got a diverse group of members, but the only thing they've got in common is the toxin gene. They produce toxin. So you can subdivide them into different groups. And the two major groups are the proteolytic. So with the proteolytic one, it's a mesophilic one. So the proteolytic, which produces protease, as you probably guess, it only grows around about 37 degrees, between 10 and 48, but optimum 37. Now, of more concern is the non-proteolytic, because what this can do is it's psychotrophic, which means it can grow at refrigerated temperatures. So with Staph aureus, for example, you can inhibit growth by just refrigerating. With non-proteolytic Clostridium botulinum, it actually can grow at refrigeration temperatures, and this is why it's responsible for more outbreaks than the proteolytic one, because we refrigerate foods, isn't it? Oh dear. So now the thing is, as we talked about, is that when we're designing foods or looking at intrinsic, extrinsic properties, you always have to consider Clostridium botulinum because of its virulence. So any foods that are above 0.92, i.e. 0.93 and above, anaerobic with low acid, you have to have a botulinum intervention step, even though the number of cases are very few a year, but you have to take care of it. So you typically, if it's anaerobic, above 0.93 or above pH 4.6, you need to have an intervention step for Clostridium botulinum. Now, as I mentioned, they are genetically diverse. The only thing they've got in common is the toxin gene. And even then, they've got different, what we call toxinotypes. So this is the toxinotype is where the toxin has the same effect, but it's kind of variation in its sequence. So we have these different groups, which foodborne botulism, and the group 2 is the psychotropic one. These are the ones that are more relevant to the food, because you can get all kinds of botulinum, wound botulinum, things like that. So these are the 2 relevant ones. And I don't expect you to be able to read this, but I'm hoping it illustrates is how diverse Clostridium botulinum is. For example, you've got Clostridium botulinum group 1 down here, which again is the sort of foodborne one. And you've even got, and distantly related is the botulinum group 3 up here. And so there's been talk about separating them out into different species and things like that, given their own species. But it's too much effort, and it'll bring large amount of confusion. So it's very diverse, but they do carry the toxin gene. So what happens then is that the toxin, botulinum toxin, literally what it does is block neuromuscular synapses. Basically it breaks the synapse connections to your muscle, which basically means it doesn't work. And in Botox, that's good because you can get rid of wrinkles. I should get some, I suppose, in a way, but anyway, it's another day. But when it's in the body, it's obviously causes a progressive paralysis. So typically what happens is that if you get botulinum, or if you ingest botulinum toxin, you'll start feeling droopy, your eyes will start drooping, then you'll get slurred speech, and eventually it reaches your diaphragm, where it stops the diaphragm moving, which basically means you stop breathing. And obviously stopping your heart's not good either, things like that. So it's a progressive illness, and it can take a few hours to come on, but then it's a very progressive decline. There was a famous outbreak a few years ago now, where somebody ingested it. And when they ingested the toxin, they started having paralysis. And the doctors at the time thought it was West Nile disease, because West Nile disease causes paralysis as well. But it's different in that West Nile disease goes from paralysis from the feet up, whereas botulinum intoxication goes from the head down. Don't ask me why. But anyway, so they left this poor patient for 6 weeks with this toxin eating away. And eventually they found it and gave the antidote. But they spent over a year in hospital, and I don't know what the outcome was. I don't think you could recover from that, but basically that's what it does. It's literally eats away at you, and it's fairly lethal. Now, the toxin itself, when it's formed, is produced in its inactive form, and it's basically combined with a heavy side chain or light side chain. So this kind of protects it so that it's only active where it's needed, i.e. the sort of synaptic junction, isn't it? So what happens is that you ingest the toxin, and it gets to your endosome of your nerves eventually after circulating the blood a little bit. And then it starts breaking the junctions down. So just to go back to first year sort of physiology, I suppose it is. These are how the muscle usually works. So what happens is your nerve endings have this junction, these snare proteins. So you've got synaptobrevin, synaptobrevin, SNAP25, or sanotaxin. And what these do is they combine to form a junction. And once a junction's formed, they produce this acetylcholine. And this acetylcholine is released, and you get a contraction. That's how we move our hands, move every other muscle, isn't it? Now, what the botulism toxin do is cut these nerve endings. And as I mentioned to you, you've got different toxinotypes. So these are the different toxins, but they have the same net effect. Net effect being that they break this junction. So you get ingestion of the botulism toxin. The light chain is cleaved from the heavy chain. And then some act on the synaptobrevin, others act on the SNAP protein and sanotaxin, and therefore your muscle becomes paralyzed. So yeah, this is just a cartoon version of it. I think you get the idea. So basically, you just remove the nerve endings, which is good if you want to get rid of wrinkles, not so good if you want to keep living, isn't it? Now, the thing is that with botulism, then there's different foods, and we'll come to those in a little bit. You can get infant botulism. So this is a very young, and with a very young, they can ingest things like honey, and honey, as you probably you do know, is collected by bees, isn't it? The bees go from one plant to the next plant, and as because botulinum exists in soil and things like that, it collects botulism spores, and those botulism spores are put into the honey, and the spores are resistant, as we talked about before. And then, people give children honey, even pasteurized honey, thinking they're doing good. But in actual fact, it's a fairly high risk of botulism. And the good thing, though, is that it's very rare. And with children, it's typically they can recover quickly. And there is a vaccine available. And so, but you wouldn't give the vaccine as you would do measles or things like that. It's more like an antidote. All right, then. So, but why do you think it is? So, if I got botulism, I'll probably be laid out. But what is it like young people? Like young people, and we're talking infants here, babies and that, toddlers. But why is that? Is it because their immune system is insufficiently developed? Is it the microbiome underdeveloped? Is it consuming high-risk foods? Is it all of those, or is it some of those? Right. So a quick check. Right. So basically, oh yeah, well done. Those who got it. Basically, how it happens is you ingest the spores in this case, and they germinate with the GI tract. And the reason why they can germinate is because the microbiome is underdeveloped. Typically with botulism spores, they'll just sit there. They won't come out if there's a lot of competition around. The immune system isn't sufficient yet to actually fight off the infection. And they do consume high-risk foods like honey, for example, which you wouldn't think of. And there's always this argument saying, well, should you give advisories to young parents saying, should you avoid honey? Well, I would suggest that you should. There's no real benefit to it. By the way, it's a honey business, isn't it? All right. So the good news, if there is good news, is that the toxin is heat liable. So whereas Staph aureus toxin, you can't destroy it. With botulism toxin, you can destroy it. And as I mentioned to you, what you tend to do is make sure that with those high-risk foods, you ensure that you've got a botulism control step, be it eradication or inhibition. So in cured meats, for example, botulism literally means in the Latin from sausage or poison sausage. And so we had nitrites. So what the nitrites do is disrupt the ferredoxin system, which is the kind of electron transport chain of the anaerobe. So it inhibits growth. And, when you hear about people taking nitrites out, like we talked about, this is why it's a good idea. The risk of botulism is there, even though we get a low risk. But anyway, thinking about food vehicles, Which is the odd one out in this group of foods to do with botulism? Is it the pasteurized carrot, nacho cheese, home canned peas, or is it your gherkin? I think that's gherkin or dill pickles, isn't it? So yeah, so just click on the one you feel is the odd one out. Move it up a bit. All right, so let's have a look. See, oh, that's interesting. So only a few of you went for the pickles. So the reason why pickles are the odd one out is they're the only one. No, dill pickles has never been associated with a botulinum outbreak. Um, the case I was just talking about with the poor person who ingested toxin, they misdiagnosed it. That was with the Bolthouse Farms carrot juice. So what they did, in infinite wisdom, is that Bolthouse, which is in California, harvested some carrots, they made the juice and they pasteurized the juice, 72 degrees C for 20 seconds. And then they marketed it. Now, the problem was it had the non-proteolytic botulinum, so they've refrigerated it, but in this case, some were left out, and the botulism grew. And when they actually sampled it, it had the highest level of toxin anyone had found, so like 30,000 units, and 6 people got affected. And as I mentioned to you, some got misdiagnosed. I think 2 died, but I think another one, I think they just got released from hospital a few years ago, and I don't think they ever recovered. So you can see what happened is that the carrots contained the botulinum, the pasteurization didn't inactivate the spores, and away you go. Temperature abuse, you get an outbreak. The nacho cheese one is a very interesting one. So this story, and if you want to read the story, you can do. So this is in a gas station in the US. And what they did is they had this sort of converted unit. And it wasn't a real nacho units, I guess. I haven't looked at them. Have a sort of container with a bag and the plastic straw comes out and you take your nacho cheese and enjoy it. Well, what they did is convert this one. They used to pour the cheese into this container. And gas stations, if you eat food from a gas station, it's not the best idea. Well, it had grit, basically soil, and it got into the dispensing part of the actual unit itself. And so it had the anaerobic conditions, the cheese to give it its growth substrate, and it caused these botulism outbreaks. And it was widespread because gas stations you would visit and go along. More recently, there was an outbreak of botulism associated with home canning, and it was peas and potatoes, I think it was. And same old story, isn't it? You get your peas, you pack them in a bit of brine, you cap them, but you don't sufficiently heat treat them. And therefore, what happens is that the anaerobic conditions, botulism can grow on peas for definite, and therefore it proliferates. Now, with pickles, the reason why they're safe is that because they're highly acidic and therefore don't support the growth. So there you go. Interesting stories all around. So typically what you'll find then is that botulism lives in the soil, in the GI tracts of fish especially. If you get vacuum packed fish, that's a big danger zone. I could tell you a story about a Toronto restaurant, but I won't do it today. So it's usually associated with those low acid foods like meat, fish, and vegetables. And, inadequately canned foods are implicated, and foods in oil. So when you see sort of go into these artisan shops and you see the garlic in oil and it's stored at room temperature, you kind of avoid it. Now, the thing is that with a non-proteolytic botulinum, because it can grow at refrigeration, there's obviously a risk that you could actually get botulism even when things are stored refrigerated. But there's certain products which are low acid. So Happy Planet soups is a good example of this. So Happy Planet soups are a product that you can store in the fridge, it's got a shelf life of about 30-40 days. And the reason why they can do that is that they actually cause a treatment called 90-10, which basically means they heat it at 90 degrees C for 10 minutes. And what this does is inactivate the non-protolytic spores because they're more heat sensitive. And therefore you can do that. And if you've got cold chain management to avoid growth of the other botulinum, it's good. So that's called 90-10 processing. But usually, typically, you have prevention in terms of adequate thermal processing. When we talked about HACCP later on, we noticed the canning industry were the first to adopt that for the good reason, because they were having these botulism outbreaks. And so when you're doing a product development, you've got to look at the high-risk foods in terms of acidity, in terms of water activity, and anaerobic. And therefore, you need to have a sort of thing in place in order to do it, be it sterilization or something else, and have nitrites to cured meats and things like that. All right, so now we'll talk about infection. So with infection, basically you're ingesting the viable cell, which then becomes colonizes your GI tract and sometimes invades. And the classic examples of these are Campylobacter, Salmonella, Listeria, Yersinia. And what you'll notice, though, is you get a lot of overlap in terms of infection and toxico-infection, because the classic model says, oh, they just ingested the colonized, and that's all they do. But a lot of them actually do produce toxins, as we'll talk about. So it gets a bit confusing, but we keep the old sort of style, if you want to call it that. So the first one is Campylobacter jejuni. And Campylobacter is a very interesting pathogen in that not only it's got a spiral shape and it's motile, but it's very sensitive. Basically, if you incubate it in the air, the oxygen can actually kill it. And as we talked about in the unit 2, I think it was, we talked about the viable but non-culturable state. And Campylobacter seems to like to enter that fairly quickly, because to cultivate it, you need to modify the oxygen to have it at a low level, not 21%, but 3 to 6%. And the reason why Campylobacter is so sensitive, it's got an enzyme called pyruvate formate lyase in the metabolic pathway, which is inhibited. And once that's inhibited, it kind of jams up the metabolism. So not only does it need microaerophilic, but it also needs high temperatures to grow, about 42 degrees C. So it really grows in food, not only because of the oxygen, also because of the temperatures, readily inhibited at refrigeration, even room temperature. And it needs, it's fastidious, which means it needs special nutrients to grow, very sensitive to oxidation stress. And you'll always find it in low numbers in food. And like I say, I've never seen an example where it can grow in a food itself. But once you ingest it, that's where its happy place is, and it proliferates. And if you have diarrhea from Campylobacter, you can recover the pathogen around about 10 to the 8 CFU per gram. It really likes to live in the body, as I say, makes itself at home. So basically, it's very virulent in terms you only need 500 cells to cause illness. And when you think about a pinhead containing 1 billion, it puts it in perspective. And what it does, it goes through the stomach, goes down to the intestinal tract, and then it'll start burying itself in the surface of the mucosa and start growing. And once it grows and sticks into place, that's where the diarrhea really starts coming, because it produces this toxin, like I mentioned to you. There's a bit of overlap between a toxico-infection. And the colonization with this cytotoxin basically causes fluids to accumulate in your lumen, and that's when the diarrhea starts. So it's kind of invasive on the mucosa, just hanging on in there as the diarrhea flows, isn't it? And in terms of symptoms, this gives you the explosive diarrhea. So if you've ever had the unfortunate sort of a case of getting Campylobacter, essentially what it is explosive diarrhea for 7 days. Sometimes bloody, which you can imagine, given the sort of forces involved. And it gives you all those classic symptoms of foodborne illness, the headaches, the chills. And typically it's a week, sometimes goes longer, but you can be an asymptomatic carrier as well. But as with lots of foodborne illness, it's not the initial infection or symptoms that's the big danger. It's basically the secondary symptoms. And in terms of Campylobacter, it can cause meningitis, an infection of the nervous system. And it can also lead to a condition called Guillain-Barré syndrome. So the thing about Guillain-Barré syndrome is that, you know, Campylobacter is associated, but it's only one of many causes. And this is where the body starts basically digesting itself, a very slow paralysis and ultimately death. So it is very, you know, despite all its sort of failings, it is one of the top foodborne illness causes, as we talked about. Kind of changes with salmonella and things like that. But the reason why it can cause Guillain-Barré syndrome is that when the immune system detects it, it produces, you know, the B cells combine. It elicits that response we talked about, you know, MHC2 on the outside, and it brings in the helper cells, the T helper cells. They release the cytokinins. That beta cell starts producing antibodies against Campylobacter LPS. But the thing is, those same antibodies can actually combine with a ganglioside on our nervous system, on the neurons. And what happens then is when you've tagged the antibody onto the ganglioside, it tags it for destruction. So your cytotoxic T cells come along and start blowing up your nerve cells, which obviously isn't good for you, is it? And that's what causes the paralysis. So, you know, that's why we're saying the immune system can be friend or foe, isn't it? And in terms of sources, it lives happily in birds and cattle in terms of, because that's where it's adapted. It doesn't cause symptoms in those animals. And it can live happily, but obviously it does cause illness in ours. But even with ours, in our case, yeah, we can be asymptomatic carriers. Certainly with poultry, up to 80%. Some people say in organic production, free range, because the mingle, up to 100%. And so poultry is the main source. But after saying that, there's other sources as well, as we'll just talk about in the next slide. But as I mentioned to you, animals don't suffer it, but the manure can contain high levels of the pathogen. So typically, poultry is the obvious one, you know, because of its association. Cattle, you know, can shed it in the manure and it can get into raw milk. And as you'll notice, raw milk outbreaks frequently have Campylobacter. Yeah, meat and, you know, beef and things like that. And if manure contaminates water, like it did in Walkerton, you know, E. coli 157 was one pathogen, but also they had Campylobacter to work with, and that can cause illness as well. So it's one of these pathogens that very low numbers, not very hardy, but he's found a strategy to actually go from one host to the next host, isn't it? So in terms of prevention, obviously adequate cooking, you know, make sure you've got a meat thermometer is good. Avoiding cross-contamination between raw and cooked meats. Washing hands, you know, if you want to do raw milk, do it, but it's best to pasteurize and chlorinating water. All right, and last question then, if whilst we might finish this. So Campylobacter is very fragile, as we talked about, but it's responsible for the most foodborne illness. But how do you think, or why do you think that is? Is it because it's high prevalence in foods, low infectious dose, rapid growth, or is it all of the above or some of the above? All right. Oh, well, it's a bit of a split decision. So essentially, it's got very high prevalence in foods. You know, you go to any poultry, you'll probably find it. Low infectious dose 500, but the reality, it doesn't grow in food. You know, I've never seen an example because of its conditions that's required, but it doesn't need to, because like when you've got 500 cells, you don't need to grow, do you? So what we'll do there, we'll leave it there then, and we'll carry on with salmonella on Friday. And as I mentioned to you, don't forget the midterm and get back if you need any sort of clarification.